Welcome back. In the last lecture, we started the solution of partial differential equations using Laplace transform first. So, there we have seen that different kind of partial differential equations are there. Second, I am talking about the second order linear equations, which are maybe of the parabolic, hyperbolic or elliptic type. We have made the classification also. So, let us continue with that. Let us take one more example of the heat equation. This is the heat equation. Solve the following partial differential equation using Laplace transform. Del u del t equals k del 2 u del x square x greater than 0 t greater than 0 with u 0 t equals u 0, which is constant when t greater than 0 and u x 0 equals 0 whenever x greater than 0. So, this is nothing but an heat equation. Please note one thing, that this problem is similar to the earlier problem. Only thing we change here is the condition. In the condition for the earlier problem, u 0 t equals f t, and for this problem you have considered u 0 t equals u 0, that is a constant value. So, your function is del u del t equals k into del u del t square del u del x square. So, del u del t, this is equals to k into del 2 u del x square. So, as I have told, the first thing what you have to do, that is your subject to u 0 t equals u 0, subject to u 0 t equals u 0 and u x 0 equals 0. These conditions are provided. As I have told you earlier, we have to take the Laplace transform on both sides of the given equation at first. So, apply Laplace transform on both sides of the given equation. Then you will obtain Laplace transform of del u del t. This you can write down by the formula s into u bar x s minus u x 0. And the right hand side, since del 2 u del x square, I am applying Laplace transform with respect to t, obviously, like the earlier problem here, applying Laplace transform with respect to t. So, that del u del t you can write down s into u bar x s minus u x 0. This is equals to k into, this will become d 2 u bar. U bar will be a function of x and s by d x square, where u bar x s is nothing but the Fourier transform Laplace transform of the function u x t. So, this by putting u x 0 is equals to 0. So, this value will be equals to 0. Once I am putting this one, so you can write down d square u bar by d x square. This is minus s by k u bar. This is equals to 0. This we got in the earlier example also. So, that the solution of this can be ordinary differential equation can be obtained very easily, m square minus s by k equals 0. So, that m will be equals to s plus s by k and minus s by k. So, that u bar equals u bar, which is a function of x and s. This is equals to, you can write down a into e power root over s by k into x plus b into e power minus root over s by k by into x. So, now your job is to first find out the values of these constants a and b. Once I found the values of the constants using the conditions, then I can obtain u bar x s, and once I have obtained u bar x s, from there directly you can write down u x t by using the inverse Laplace transform. Now, as x approaches 0, as x approaches infinity, your value of u will be equals to 0. As x approaches infinity, value of u equals 0. Since u equals 0, so therefore, you can tell that value of u bar will also be 0. And if you substitute in the earlier equation 1, that u bar is equals to 0 whenever x approaches infinity, From there you will obtain a equals to 0. So, using this condition u bar equals 0, as x approaches infinity, your u approaches 0. From there we are saying u bar equals to 0, and if you substitute here value of x and u bar, you will obtain that a is equals to 0. And also, so therefore, you can write down your u bar xs, this is nothing but b into e power minus root over s by k into x. So, now I have to find out the value of b also. Since u bar this equals 0, you can tell that u bar 0 s, this will be equals to b, which implies that, which implies what? U bar 0 s means Laplace transform of u 0, where u 0 is constant, or you can tell Laplace u 0 you can bring outside Laplace transform of 1, and Laplace transform of 1 is 1 by s. Therefore, u bar 0 s is equals to u dot by s. Here, since u dot is a constant, so u dot you can take out outside, and u dot into Laplace transform of 1 you can write down. So, from here you can write down b equals u naught by s. So, once I obtained u naught, so now I can write down u bar x s equals u naught into e power minus root over s by k x by your s. So, once I have obtained u bar into as a function of x and s, then you can find out what is your u x t using the inverse Laplace transform. So, that you can write down u x t equals u naught will come outside into Laplace inverse of this quantity e power minus root over s by k into x divided by s. And this equals, if you simplify it, u into L inverse, you can write down Laplace inverse of e power minus x by root k into root s divided by s. If you recall, this is nothing but Laplace inverse of this is nothing but complementary error function of x by 2 root k t, x by 2 into root k t. So, therefore, u x t equals u naught, this is your u naught into complementary error function of x by twice into root over k t. So, effectively what we have done here, you are initially you have the solution, you have the differential equation. From the differential equation, basically what you are doing, you are taking Laplace transform on both sides, then you will your given partial differential equation will be transformed to a second order ODE, and you are finding the solution of the second order ODE in terms of u bar, that is Laplace transform of the u x t, and the solution will contain, solution of ODE will contain two arbitrary constants. Using the initial conditions, you can find out the solution, you can find out the values of those arbitrary constant, and you can find ultimately a form like this, u bar equals u naught into some function of s into x. And from there, by using inverse Laplace transform, you can find out u x t equals u naught into Laplace inverse of this, and whose value is known to you, that is u naught into complementary error function of x by 2 into root over k t. So, that thing for this particular problem, what we have done, directly we have written the solution u x t equals Laplace inverse of root over s by x into Laplace transform minus root over s by k into x into Laplace transform of u naught, and Laplace transform of a is a by s, where a is constant, by that way you are writing u x t. So, and this is nothing but the Laplace inverse of this function is the complementary error function of a by 2 root t, and therefore, you are getting the value of this one as complementary error function of x by 2 root over kt. Here you see we have written Laplace inverse of e power minus a into root s by s. This is equals complementary error function of a by 2 root t. This we have done earlier whenever we have studied the Laplace transform. So, by this way you can solve this problem. Now, let us take the another problem, that is we want to solve the PDE del 2 u del t square equals s square del 2 u del x square x greater than 0, t greater than 0, with the conditions that u x 0 equals 0, u t x 0 equals 0 when x greater than 0, u 0 t equals f t, and u x t as x approaches infinity equals 0. This comes basically from the physical condition that as x approaches infinity, the value of the function approaches 0 when t is greater than 0. If you recall, the equation del 2 u del t square equals s square del 2 u del x square is nothing but the wave equation. So, basically we are trying to find out the solution of wave equation using the Laplace transform. So, here your equation is this one del 2 u del t square equals s square into del 2 u del x square, where your x greater than 0, t is greater than 0. I am not writing the initial condition. Now, you take Laplace transform on both sides with respect to t. You may ask that why not we are doing it with respect to x also. So, with respect to x, whether it is satisfying the initial conditions or not, that you have to check. With respect to t, the initial conditions, whatever has been provided to us, we can use this and we can find the solution of this one. And that is the reason here we are taking the Laplace transform on both sides with respect to t. So, basically although both the variables x and t are greater than 0, but depending upon the initial supplied initial condition, we have to decide we will take Laplace transform with respect to which independent variable, either x or t. Like in this particular example, we are doing it with respect to t. So, once we are taking the Laplace transform, so Laplace transform of del 2 u del t square equals a into Laplace transform of del 2 u del x square. Here please note that I am taking the Laplace transform with respect to t. Since I am taking the Laplace transform with respect to t, therefore, I have to use the formula Laplace transform of del 2 u del t square will be equals to, which from here you can get s square into u bar x s minus s into u x 0 minus u t x 0. This already we have done in the last lecture, we have done it, that Laplace transform of del 2 u del u t square is equals to s square into u bar x s minus s u x 0 minus u t into x 0. This is equals to s square into Laplace transform of del 2 u del x square, where you have taken the Laplace transform with respect to t only, not with respect to x, and in that case this will be simply d 2 u bar into d x square. So, the variable with respect to which one you are taking the Laplace transform, for that the second order derivative, Laplace transform of the second order derivative will come as s square u bar minus s u x naught minus u t x naught equals s square into d 2 u bar d x square on this side, because you are not taking Laplace transform with respect to x. Now, the value of u x t is known to us, and value of u x naught and u t x naught is known to us. Actually, if you remember from the earlier one, u x 0 is 0 and u t x 0, this is also 0. U t x 0, this is also 0 and it is given to us. And that is the reason now you can understand why we are taking the Laplace transform with respect to t, because if I would have taken Laplace transform with respect to x, then there would have the function s u 0 t, but the value of u 0 t is not given, or u x 0 t, that is also not provided. Since these values are provided initial conditions, that is the reason we are taking the Laplace transform with respect to t. So, basically since both are 0, therefore, this term will be equals to 0, this term also will vanish. So, that directly you can write down d square u bar dx square minus this will be s square will go on that side. So, s square by a square into u bar x s, this is equals to 0. So, this is a square, basically s square by a square into u bar x square, this equals 0. So, this is again, so effectively what is happening here, I am repeating this case, that you have the second order PDE over here, whose solution you want to find out using Laplace transform. What you are doing here, you are taking the Laplace transform, and this second order PDE basically is converted into a second order ODE, whose solution is very well known to us, because m square minus a square by a square equals 0. So, that it is roots are s by a and plus s by a and minus s by a. Very easily I can find out what will be my u bar. So, first m is, if I have to say, I have to tell solution of this problem will have 3 steps. In the first step, whenever you are taking the Laplace transform on the second order PDE using the Laplace transform and by substituting the initial conditions, you are basically converting the ODE PDE into a second order ODE. Then I have to, second step will be to find the solution of this second order ODE, and as we know, finding the solution of ODE is much easier compared to the second order PDE. So, now the solution of this directly you can write down u bar x s, this is equals to a into e power s x by a plus b into e power minus s x by a. Say this is equation 1. This I got it directly from here, that u bar, since the root of the equations are s by a and minus s by a, from there directly you can write down u bar s x x s equals a e power s x by a plus b e power minus s x by a. Your next job is to find out the value of these coefficients, that is a and b. To find out the values of these coefficients, you have to use the conditions supplied, like one condition has been given as u x t approaches 0 as s approaches infinity. So, from here what you can tell, u x t approaches 0 as x approaches infinity. So, if I take the Laplace transform on both sides of this, then from here I can tell that u bar x s, of course, Laplace transform with respect to t, approaches 0 as x approaches infinity. So, as x approaches infinity, u bar x s approaches 0. So, if I substitute it in 1, that is from 1, if I substitute it, what I will obtain, u bar x s approaches 0 whenever x approaches infinity. So, that the second term of equation 1 will vanish, and from that left hand side is 0. So, e to the power s x by a cannot be 0, therefore, your a is equals to 0. So, 1 you got it, that a equals 0, one coefficient's value you obtained. So, by substituting this u bar x s approaches 0 as x approaches infinity, substituting this thing in equation 1, we are obtaining a equals 0. What is the second equation is given to us is u 0 t, this is equals to f t. This is given to us, u 0 t equals f t. So, if I take Laplace transform on both sides with respect to t, then I will obtain on the left hand side u bar 0 s. This is equals Laplace transform of f t is nothing but 0 to infinity f t into e power minus s t dt, and this is nothing but I can denote it as f bar s, where basically f bar s is the Laplace transform of the function f t. This value I cannot evaluate, since the value of the function f t is not known to us. Now, substitute this thing again in this equation 1, u bar x s equals a into this plus b into this. So, if you substitute x equals 0, already a has vanished, here e power part will be vanishing. So, that you can obtain from 1, again from 1 you can say that b will be nothing but f bar x s, f bar s. So, from here what is happening, u bar 0 s, I am saying it is f bar s. So, if I substitute in equation 1, a is already 0, if x is 0, so e power term will not be there. So, only on the right hand side b will be there, and left hand side it is u bar 0 s, which is f bar s. So, that b equals f bar s. So, now I obtain the value of both, that is a and b, and I can write down u bar x s, this is nothing but e power minus s x by a into f bar s. This I can write down u bar x s, this is equals minus e power minus s x by a into f bar s. So, this is basically the second step. So, first step was to find out the solution of the ODE, which I derived from the PDE. Using the Laplace transform, I converted the PDE into the second order ODE. I am finding the solution of that, and that I obtained in the form of equation 1, and this was the first step. In the second step, what I am doing is I am finding the values of the coefficients using the conditions provided, and I am finding the solution as e power minus s a s x by a into f bar s. This is my second step. Now, the third step is, from this always you can write down using the inverse Laplace transform u x t, this is equals Laplace inverse of e power minus s x a s x by a into f bar s. We can write down this thing, u x t is this one. So, that your u x t will be Laplace inverse of e power minus s x by a into f bar s. Is it familiar to us? Can I write down directly something? Laplace inverse of this one is equals to, you can tell that function of t minus x minus a whenever t is greater than x by a, when t is greater than x by a, and it is equals to 0 if t is less than x by a. So, I am not going to how I am finding the Laplace inverse of this. Using the properties of Laplace transform, always you can write down e power f of t minus x by a, because coefficient of s is minus x by a. So, this I can write it as function of t minus x by a whenever t is greater than x by a, and it is 0 whenever t is less than x by a. And this equals, again I can write it as function of t minus x by a into h of t minus x by a. What is h of t minus x by a? H of t minus x by a is nothing but the Heaviside with unit step function. So, for t greater than x by a, value of this h t x minus a, that is Heaviside unit step function, this is equals 1, and for t less than x by a, the value is equals to 0. So, you see the advantage of this. I have used a general function f t. In my condition, I have used the condition this thing u 0 t equals f t. So, now in place of f t you put any value directly from this solution, you can obtain the solution of the given equation itself, function of t minus x by a. So, for any f t I do not have to resolve the problem again, simply substitute the value of f t with the appropriate function and you will obtain the result. And this was the third step, that once I have obtained the inverse u bar x s by using the inversion formula, I have to obtain the value of u x t, and by that way I am writing this particular equation f of t minus x by a into h of t minus x by a. So, quickly if we go through this one, your original problem was this, that find the solution of this wave equation by doing with the wave equation del 2 u del t square equals a square del 2 u del x square, with the conditions u x 0 0, u t x 0 equals 0 for x greater than 0 and u 0 t equals f t, and limit x approaches infinity u x t equals 0 whenever t is greater than 0. So, as I told, I am taking Laplace transform on both sides of the given equation with respect to t. Once I am doing it with respect to t, on the left hand side Laplace transform of del 2 u del t square, this will be equals to a square u bar x s minus s u x 0 minus u t x 0 from the formula which I have given in the last lecture. This is equals a square d 2 u bar d x square del 2 u del x square, since it is there, and I am taking the Laplace transform with respect to t, therefore, Laplace transform of del 2 u del x square equals d square u bar by d x square, where u bar is nothing but the Laplace transform of u x t. Now, I know from the conditions u x 0 is 0, u t x 0 is 0. If I substitute this, the equation will be converted into this one, which is nothing but a second order ODE, and the solution of this directly I can write down u bar x s equals a e power s x by a plus b e power minus s x by a, where I have to find out the values of the constants a and b. So, one condition I know, u x t approaches 0 as x approaches infinity. This was your equation 1. So, once I know u x t approaches 0 as x approaches infinity, therefore, u bar x s approaches 0 as x approaches infinity. If you substitute in 1, you will find that the second term vanishes, and for the first term then a equals 0, since the e power term cannot vanish. So, I have another condition u 0 t equals f t. From here I can write down u bar 0 s equals Laplace transform of f t, taking Laplace transform on both sides actually. So, Laplace transform of 0 to infinity this, which I am denoting as f bar s. If I substitute this in equation 1, again I will obtain b equals f bar s. Therefore, value of the constant a equals 0 and b equals f bar s. So, my u bar becomes e power minus s x by a into f bar x. So, u x t I can write down using inversion as Laplace inverse of this function, and u x t equals, I am writing e power this into f bar s, and whose value is equals to function of t minus x by a if t greater than x by a and 0 for t less than x by a, which I can write it in the form of function of t minus x by a into h of t minus x by a, where h is the Heaviside unit step function. So, we have solved this problem for general f t, and for any function f t I do not have to resolve the problem. Simply by changing the value of f t I can get the solution or the value of u x t. So, in this lecture we have solved the problems of heat equation and the wave equation applying Laplace transform. I hope it is clear that using the Laplace transform, how to find out the solution of different kind of partial differential equation, the steps. So, please remember it consists of 3 steps. In the first step, the PDE is converted into a second order ODE using Laplace transform. Then the second step, I am finding the solution of that ODE. Since the second order ODE, therefore, the solution will have two constants and I have to find out the values of those two constants. By that way, I am finding u bar as a function of x and s, and from there, using the third step, using inverse Laplace transform, I am finding u x t by taking the inverse Laplace transform, and ultimately I will obtain the required solution.